our second exercise is basically based upon the fundamental theorem of arithmetic. So before solving the questions in this exercise, let us have a quick recap of what fundamental theorem of arithmetic is. Now, every composite number can be expressed as a product of primes, and their factorization is unique apart from the order in which factorization occurs. That is, prime factorization of a natural number is unique. Now, after this, we have to deal with two terms, that is HCF and LCM, in the fundamental theorem of arithmetic. So now what HCF is? It is the product of the smallest power of each common factor in the numbers. Then LCM, it is the product of the greatest power of each prime factor involved in the numbers. Now, after this, we have a very important formula, that is product of two numbers is equal to HCF multiplied by LCM. So these were the some main points or the some important points that we have to keep in mind in the theorem of arithmetic, and basically in our exercise 1.2. So let's start with our first question. Okay, this is our exercise 1.2. Our first question is, express each number as a product of its prime factors. For this question, I will be solving three parts, that is first, third and fifth. So let's proceed. Our first part is 140. We have to express this number as a product of its prime factors. Now, we can solve this in two ways. The first one is the very simple one that we are doing from our early classes. Now again, it's 2 and 35, then we have 5 and 7, then 7 and 1. Now for this, 140 is equal to 2 multiplied by 2 multiplied by 5 and multiplied by 7. After simplifying this, we will be writing 2 square multiplied by 5 multiplied by 7. Now our second method is the one that I use, that is this one. 75, 35, it's 2, then 5, then 7, and then obviously that would be 1. So I will be leaving this here only. Now we can use either of the methods, but to have a good impact on the examiner, you can use this method. Now our third part is 3825. Now 3825. Now 3, then 1275, then again 3, 425, then we have 5 and 85, then we have 5 again and 17. Either you can leave it here or we can solve it in one more step, that is still here. Now 3825 is equal to 3 multiplied by 3 multiplied by 5 multiplied by 5 and 17. Then you can write it as 3 square multiplied by 5 square multiplied by 17. Proceeding ahead, our fifth part is 7429. 7429, then 17, 437, 19, 23, then on table of 23, 1. So 7429 is equal to 17 multiplied by 19 multiplied by 23, and the power of each number here is 1. Okay, now our second question is find the LCM and HCF of the following pairs of integers and verify that LCM multiplied by HCF is equal to product of the numbers. In this question, we have to find the LCM and HCF of the pair of numbers. Now, our first part is 26 and 91. Now, 26, we will be solving them one by one. Now, 13, then 13 and 1. So, 26 is equal to 2 multiplied by 13. Then 91, 7 and 13, then 13. Then 91 is equal to 7 multiplied by 13. Now our HCF here is 13 because it is the common number in both the factorizations and it is with the smallest power, that is 1. So now our LCM would be 2 multiplied by 7 multiplied by 13. Now we will be taking the pair of 13 and 13 would be written once only. Now after multiplying this we get 182. Now verification. LCM multiplied by HCF is equal to product of numbers. For verification, we'll see LCM. Our LCM was 182 multiplied by our HCF, that was 13, is equal to product of numbers. 26 multiplied by 91. 182 multiplied by 13 is 2366 and 26 multiplied by 91 is 2366. Now as our product of our HCF and LCM is equal to product of numbers, so we'll write hence verified. I'll be leaving the next two parts for you. Now we'll be proceeding to the third question. That is, find the LCM and HCF of the following integers by applying the prime factorization method. We have to find the LCM and HCF of the following integers by applying the prime factorization method. So, the first part is 12, 15 and 21. 12, 6, then 3, then 1, then we have 15 as 5, then on 5, 1, then we have 21 as 3, then 1. Now 12 is equal to 2 multiplied by 2 multiplied by 3 is equal to 2 square multiplied by 3. 15 is equal to 3 multiplied by 5 and 21 is equal to 3 multiplied by 7. Our HCF is 3 because it is common in every prime factorization and it is with the smallest power, that is 1. So our HCF is 3 and our LCM is 2 square multiplied by 3 multiplied by 5 multiplied by 7. So our LCM is equal to 420. So this was our third question. Proceeding to our fourth question, that is, given that HCF of 306 and 657 is 9, find the LCM of the same numbers. Okay, we are given HCF of 306 and 657 as 9. we have to find LCM of 306 and 657. Now we will be using the formula HCF into LCM is equal to product of numbers. Now our HCF is 9 and LCM is, and we will be writing LCM as it is, and product of numbers is equal to 306 multiplied by 657. LCM is equal to 306 multiplied by 657 divided by 9. Okay, 3, then 1, 0, 2, then again 3 and 34. Now LCM is equal to 34 multiplied by 657. So our LCM is equal to 22,338. This is our LCM. Now our next question, that is the fifth one, is check whether 6n can end with the digit 0 for any natural number n. 6n can end with the digit 0 for any natural number n. Now 6 is equal to 2 multiplied by 3. Therefore 6n is equal to 2 multiplied by 3n. Now since we do not have 5 as the factor in 6n, therefore 6n cannot end with digit 0. We will be writing, since we do not have 5 as a factor in 6n, thus 6n cannot end with digit 0. Now our sixth question is, explain why 7 multiplied by 11 multiplied by 13 plus 13 and 7 multiplied by 4 multiplied by 3, 2, 1 plus 5 are composite numbers. We have to show these numbers as composite. Now composite numbers are the ones which have more than 2 factors. So here we will be taking 13 as common. 13 multiplied by 7 multiplied by 11 multiplied by 1. Now as we have taken 13 from here also, so now we will be writing multiplied by 1. So there exist 3 factors for 7 multiplied by 11 multiplied by 13 plus 13. Thus, it is a composite number. Now for this we will have, as we have 5 common here, so 5, 7 multiplied by 6 multiplied by 1 multiplied by 4, then 3, 2 and 1. Then 5 multiplied by 7 multiplied by 6, 1, 4, 3, 2, 1 and 1. So here also there exist 3 factors for 7 multiplied by 6 multiplied by 5, 4, 3, 2, 1 plus 5. Thus, it is a composite number. Proceeding to our 7th question, we have, there is a circular path around a sports field. Sonia takes 18 minutes to drive 1 round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? So here we will be finding the LCM for this question. So let's see the question. Time taken by Sonia for one round, 18 minutes. Time taken by Ravi for one round is 12 minutes. So we have 18 and 12. So 18 and 12 will have 9 and 6, then 9 and 3, then 3, again 3. Now LCM of 18 and 12 is 2 square multiplied by 3 square is equal to 36. So LCM of 18 and 12 is equal to 36. That's the answer. And in the end we will be writing that Ravi and Sonia will meet after 36 minutes. Therefore, they will meet after 36 minutes. Now we have completed our second exercise and moving ahead for our third exercise. Now our exercise 1.3. The first question is prove that root 5 is. For the first question, let root 5 be a rational number. Therefore, root 5 is equal to a upon b. Here, a and b are co-primes. Therefore, b root 5 is equal to a. Now squaring both sides, we have 5b square is equal to a square. Now 5 divides a square. Now 5 divides a. As 5 divides a square, this implies 5 divides a. Therefore, a is equal to 5c. Okay, we'll be taking this as equation 1 and this as equation 2. Now, a is equal to 5c for any number c. Now, putting 2 in 1, 5b square is equal to 25c square, or b square is equal to 5c square. This implies 5 divides b square. Also 5 divides b. Therefore, a and b have 5 as their common factor. Now this contradicts our supposition. Therefore, root 5 is an irrational number. Hence, proved. Our second question for this exercise is prove that 3 plus 2 root 5 is irrational. Let 3 plus 2 root 5 be a rational number. Therefore, 3 plus 2 root 5 is equal to a upon b. Here, a and b are co-primes. Now 2 root 5 is equal to a upon b minus 3. 2 root 5 is equal to a minus 3b upon b. Root 5 is equal to a minus 3b upon 2b. Therefore, this implies integer minus integer upon integer. How? A is an integer, 3b is an integer and 2b is also an integer. So, this implies that root 5 is a rational number. But we also know that root 5 is an irrational number, so this again contradicts our supposition. Therefore, 3 plus 2 root 5 will be irrational. So, it means root 5 is a rational number, but we know root 5 is irrational. Thus, 3 plus 2 root 5 is irrational, hence proved. Now I'll be solving the first part for our third question, that is prove that the following are irrationals, and our first part is 1 upon root 2. Now let 1 upon root 2 is rational number. Therefore, 1 upon root 2 is equal to a upon b. Here, a and b are co-primes. Now, b upon a is equal to root 2. Here, b upon a is a rational number, but root 2 is irrational. And we also know that rational number is not equal to irrational number. Therefore, this contradicts our supposition. Therefore, 1 upon root 2 is irrational, hence proved. Proceed to our fourth exercise. Our first question is, without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating repeating decimal expansion. Okay, before starting this exercise, let's have a quick recap. For any rational number p upon q, factors of q are in the form 2n multiplied by 5m. Then the decimal expansion of the given rational number is terminating, otherwise non-terminating and repeating. Okay, so for our first question, the first part is 13 upon 3125. Okay, as we have discussed the first question, that what it asks us, let's see the second question also. Now write down the decimal expansions of those rational numbers in question 1 above which have terminating decimal expansions. So in the first question, we have been asked to see that which rational numbers will have terminating and non-terminating repeating decimal expansions without actually performing the long division. Then in the second question, we are asked to find their expansions. So we'll be solving both the questions in a single go. Now for our first question, for our first part, 13 upon 3125, it's p upon q. Now for Q we'll be having 5, 625, then 5, 125, then again 25, then 5 and 1. So 3125 is equal to 5 multiplied by 5 multiplied by 5 multiplied by 5 and 5 is equal to 5 raised to power 5 or 2 raised to power 0 and 5 raised to power 5. Any number having power 0 is taken as 1. Therefore, 13 upon 3125 is a terminating decimal expansion. Now, if it is terminating decimal expansion, let's find out its decimal expansion. So, 13 upon 3125 is equal to 13 upon 5 raised to power 5. Therefore, 13 upon 5 raised to power 5 multiplied by 2 raised to power 5 and 2 raised to power 5. We will be having 416 upon 10 raised to power 5. So this will be 0.00416 will be our answer. Our third part is, I'll be solving only 3 parts, that is first, third and the fifth one. So our third part is 15 upon 16, it's equal to P upon Q, 1600 to 800, 400, then 200, then 100, then 50, then 25, 5 and then 1. Now 1600 is equal to 2 raised to power 6 multiplied by 5 raised to power 2. Now, therefore, 15 upon 1600 is of the form 2 raised to power n, 5 raised to power m. Therefore, it is a terminating decimal expansion. It is a terminating decimal expansion. Let's find out its decimal expansion. Now 15 upon 1600 is equal to 15 upon 2 raised to power 6 multiplied by 5 raised to power 2. Therefore, 15 multiplied by 5 raised to power 4 upon 2 raised to power 6, 5 raised to power 2, 5 raised to power 4. We get 15 multiplied by 5 raised to power 4 upon 2 raised to power 6 multiplied by 2 raised to power 6 is equal to 9375 upon 10 raised to power 6. Therefore, 937,500. Okay. Now 0.009375 is our answer. Now our fifth part is 29 upon, it is equal to P upon Q. Now 343, 749, 7, 7 and then 1. Now 29, Q is equal to 29 is equal to 7 raised to power 7 into 7 into 7 is equal to 7 cube. Therefore, 29 upon 343 is not a terminating decimal expansion. Why? because it is not of the form 2n multiplied by 5m. Okay guys, this was all for our today's video. If you have any doubts regarding any of the topics, just go on the link that is coming on the screen and watch my videos regarding those topics. Okay, so if you like my video and feel the content to be useful, just hit like to my video and subscribe to my channel. Bye guys.